Before you relax, let your mind settle on one quiet question. If you were to leave Earth tonight and never stop moving, following only the real laws of physics and the limits of the human body, where would your lifetime actually end? Not where imagination takes you, but where time, speed, and biology finally say no. If this kind of question slows your thoughts and draws you deeper gently like this video, it helps others discover it too. Tell me in the comments where you're listening from as you begin this journey. And if you want more scientifically real, sleep-calm explorations that turn curiosity into rest, subscribe now and travel farther with every night. You begin by noticing something simple and familiar, your own sense of time. You are aware of days passing, years accumulating, and the quiet fact that a human life, even a long one, unfolds over a limited number of decades. This awareness is not heavy or dramatic. It is simply factual. On average, a human lifetime spans roughly 80 years, measured by the steady orbit of Earth around the Sun. Every question about travel, whether across an ocean or into space, must begin here, anchored to the amount of time a living body can experience. When you think about space, your mind may instinctively reach for distance first. You imagine how far away something is, how many kilometers separate one place from another. On Earth, distance feels manageable. You cross a room in seconds, a city in minutes, a continent in hours. These experiences train your intuition, but that intuition does not scale easily beyond the planet. Space forces a recalibration, one grounded not in imagination, but in measurement. Astronomers begin with the same unit you already know, the kilometer. A kilometer is defined by physical standards and used universally. Earth itself is about 12,700 kilometers across at its widest point. Light, which travels faster than anything else known, moves about 300,000 kilometers every second. Even at that extraordinary speed, light takes more than 1/10 of a second to cross Earth's diameter. This is the first gentle signal that space operates on unfamiliar scales. As your attention moves outward, kilometers quickly become impractical. The average distance between Earth and the Moon is about 384,000 kilometers. This number is precise, measured by bouncing laser pulses off reflectors left on the lunar surface. Light takes just over 1 second to make that journey. Space agencies use this distance routinely, and it already stretches beyond everyday human experience. The distance between Earth and the Sun is much larger, averaging about 150 million kilometers. To manage this scale, astronomers define a new unit, the astronomical unit. 1 astronomical unit represents the average distance between Earth and the Sun. This unit is not abstract. It is tied directly to orbital motion and measured through radar ranging and celestial mechanics. Light takes about 8 minutes to travel 1 astronomical unit, a fact confirmed daily by communication delays with spacecraft near the Sun. At this point, distance and time begin to intertwine naturally. When you say the Sun is 8 light minutes away, you are describing both how far it is and how long information takes to travel between you and it. Space does not separate these ideas. Movement through space always unfolds through time, and no object with mass can avoid that relationship. As you continue outward, even astronomical units become unwieldy. The outer planets orbit tens of astronomical units from the Sun. Neptune, the farthest major planet, averages about 30 astronomical units away. Sunlight there is faint, not because the Sun changes, but because energy spreads out over increasing distance. This fading follows precise physical laws, measured and confirmed through observation. Beyond the planets lies interstellar space, the region between stars. Here, astronomers adopt another unit, one defined entirely by time. A light year is the distance light travels in 1 year, moving through vacuum at its constant, measured speed. 1 light year equals about 9.4 trillion kilometers. This number is not meant to be imagined visually. It is meant to be used mathematically to compare distances far beyond the solar system. The nearest star to the Sun, Proxima Centauri, is about 4.2 light-years away. That means the light you see from it tonight began its journey more than 4 years ago. The photons arriving at your eyes left their source before you reached your current moment. This is not speculation. It is measured through stellar parallax, spectroscopy, and long-term observation. At this scale, the limits of a human lifetime become impossible to ignore. Even if you could travel at the speed of the fastest spacecraft humans have ever built, which is tens of kilometers per second, reaching another star would take tens of thousands of years. These are not pessimistic estimates. They are direct consequences of speed, distance, and time interacting under known physical laws. Your lifetime becomes the fixed variable. You cannot stretch it indefinitely, and you cannot bypass time. Biology sets boundaries through aging, cellular limits, and environmental tolerance. Physics sets boundaries through energy requirements and maximum achievable speeds. Together, they define a narrow window of possibility. It is important to understand that this window is not imposed by a lack of imagination. It is imposed by evidence. Every spacecraft trajectory, every measured velocity, every biological study of long-term exposure to space contributes data. This data consistently shows that travel must be evaluated not by where you wish to go, but by what duration your body and machines can sustain. You may notice that space travel discussions often focus on destinations: Mars, Jupiter, distant stars. Yet, from a scientific perspective, time is always the more fundamental constraint. Distance alone is meaningless without speed, and speed is meaningless without duration. This is why astronomers and engineers describe missions in years rather than kilometers. The Voyager spacecraft offer a clear example. Launched in the late 20th century, they travel faster than any human-made object before them. After decades of motion, they have only just reached the outer boundary of the Sun's influence, a region known as the heliopause. This boundary lies more than 100 astronomical units away. Reaching it took over 40 years. During those decades, the spacecraft did not slow down significantly. They simply moved through an immense volume of space where even high speed produces slow progress relative to cosmic scales. This is not failure. It is measurement made visible. When you align this reality with a human lifespan, the scale difference becomes unmistakable. 40 years is half a lifetime, spent reaching a boundary that is still part of the Sun's neighborhood. No human could ride alongside such a probe without confronting the limits of aging, radiation exposure, and resource depletion. Radiation is another reminder of scale. Outside Earth's magnetic field, energetic particles from the Sun and distant supernovae move freely. Their intensity is measured precisely by detectors on satellites and probes. Long-term exposure damages DNA, increases cancer risk, and degrades materials. Shielding adds mass, which increases energy requirements, which further constrains speed. Each factor reinforces the same conclusion through independent evidence. As you sit with these facts, something subtle happens. Space stops feeling like an empty expanse waiting to be crossed and begins to feel like a physical environment with rules. Those rules are consistent, repeatable, and indifferent to desire. They do not rush and they do not pause. They simply operate. Understanding this does not shrink human curiosity. Clarifies it. When you know the scale honestly, questions become sharper. How far can you go without exceeding biological limits? How long can systems operate without resupply? What distances make sense to discuss in terms of lived experience rather than abstract measurement? The concept of a meaningful distance emerges here. A meaningful distance is not the farthest place imaginable. It is the farthest place reachable within the span of awareness, memory, and survival. It is a distance that allows you to remain a participant rather than a historical footnote. Within this framing, even the moon takes on renewed significance. A 3-day journey at current speeds, it remains the farthest place humans have physically traveled. That journey fits comfortably within human time perception. Mars, by contrast, requires months of travel each way, with launch windows dictated by orbital mechanics. These windows are calculated precisely, using Newtonian gravity refined by relativistic corrections. You begin to see that space is not arranged for convenience. Planets do not wait in fixed positions. Orbits shift, alignments change, and travel opportunities open and close predictably but inflexibly. This predictability is what allows missions to succeed, but it also imposes patience. Patience becomes a scientific requirement. You cannot rush an orbit. You cannot compress distance without increasing speed, and you cannot increase speed without increasing energy. Energy itself must be carried, generated, or extracted, all of which are governed by physical limits tested in laboratories and flight systems. As your awareness settles, the immensity of space feels less overwhelming and more structured. It is vast, but not chaotic. It is measured, charted, and described with increasing precision. Humans understand it not by crossing it freely, but by observing it carefully. Your lifetime sits within this structure as a defined interval. It is long enough to witness technological change, to send instruments outward, and to receive signals across billions of kilometers. It is not long enough to personally bridge interstellar distances. This distinction is not discouraging. It is informative. Within one lifetime, experience is shaped by proximity. The regions that matter most are those where time, distance, and survival overlap. These regions form a bubble around Earth, extending outward in ways that can be calculated rather than guessed. As you rest with this understanding, space becomes quieter. Not smaller, but calmer. You are no longer trying to grasp everything at once. You are simply aligning your sense of time with the measured scale of the universe, letting distance reveal itself at a pace that matches what a human life can hold. In this stillness, a new kind of curiosity arises, one focused not on how far space extends, but on how motion, speed, and endurance quietly determine what parts of that vastness can ever be personally reached. You begin with motion as you know it from daily life. You walk, you ride, you fly, and each movement has a speed attached to it. Speed is simply distance divided by time, a relationship so basic it feels almost invisible. Yet when motion leaves Earth, that simple idea unfolds into a complex, carefully measured reality shaped by gravity, energy, and mass. On Earth, speed is often limited by friction and terrain. In space, friction nearly disappears, but gravity never does. Every object with mass pulls on every other object. This universal attraction governs how fast something must move to stay in orbit, to escape a planet, or to travel between worlds. These speeds are not chosen. They are calculated from physical laws that have been tested repeatedly through observation and experiment. The first important speed is orbital velocity. To remain in orbit around Earth without falling back or drifting away, an object must move sideways fast enough that its forward motion matches the curvature of Earth beneath it. Near the planet's surface, this speed is about 7.8 kilometers per second. At this velocity, a spacecraft circles Earth roughly every 90 minutes. Astronauts aboard space stations experience continuous free fall, not because gravity disappears, but because their forward speed keeps them perpetually missing the ground. Reaching orbital velocity already demands enormous energy. Rockets must accelerate a spacecraft from rest to thousands of meters per second in just minutes. Most of the fuel burned during a launch is spent overcoming gravity and atmospheric drag before orbit is even achieved. This is why leaving Earth is one of the most energy-intensive steps in any journey. Beyond orbit lies escape velocity. This is the speed required to break free from Earth's gravitational pull entirely, without further propulsion. Near Earth's surface, escape velocity is about 11.2 kilometers per second. This number is derived directly from Earth's mass and radius and confirmed through countless launches. Once a spacecraft exceeds this speed, it will not fall back unless acted upon by another force. Human-made objects have reached escape velocity many times. Missions to the Moon, planets, and beyond all begin this way. Yet even escape velocity does not mean unlimited speed. It only means Earth no longer dominates the motion. The Sun's gravity quickly becomes the primary influence, shaping the path through the solar system. As you shift perspective outward, heliocentric speed becomes more relevant. Earth itself orbits the Sun at about 30 kilometers per second. When a spacecraft leaves Earth, it already carries this orbital motion with it. This inherited speed is crucial. Space travel often involves adding or subtracting velocity relative to Earth's motion rather than starting from zero. This is where gravity assists enter the picture. A gravity assist uses the motion and gravity of a planet to change a spacecraft's speed and direction without using additional fuel. The physics are precise and conservative. Momentum is exchanged between the spacecraft and the planet, though the planet's immense mass means its change is immeasurably small. The Voyager spacecraft provide clear examples. Launched in the late 1970s, they used multiple gravity assists to gain speed. Voyager 1 currently travels at about 17 kilometers per second relative to the Sun. Voyager 2 moves slightly slower. These speeds were not achieved through engines alone, but through careful planning and celestial alignment. New Horizons, launched in 2006, achieved an even higher heliocentric speed after a gravity assist from Jupiter. It travels at about 14 kilometers per second away from the Sun, though its initial Earth relative speed during launch was higher. This mission reached Pluto in under 10 years, a journey that would have taken decades without gravity assists. These numbers represent the upper range of what chemical rockets combined with gravity assists can achieve. They are not estimates. They are measured continuously through radio tracking and Doppler shifts. Every meter per second is accounted for. When you compare these speeds to the scale of space, their limits become clear. At 17 kilometers per second, a spacecraft travels about 500 million kilometers per year. That sounds vast, yet it equals only about 3 astronomical units annually. Even at this remarkable pace, crossing the solar system takes decades. For humans aboard a spacecraft, speed alone is not the only concern. Acceleration matters just as much. Human bodies tolerate acceleration only within certain limits. High acceleration causes stress on the cardiovascular system, bones, and organs. Launch profiles are designed to keep acceleration within survivable ranges, usually a few times Earth's gravity. Sustaining acceleration for long periods would increase speed dramatically, but it would also require continuous thrust and immense energy. Chemical rockets cannot provide this. Their fuel is consumed quickly, producing a short burst of acceleration followed by long coasting phases. This leads to an important realization. Most of a space journey occurs at constant speed. Once engines shut down, motion continues unchanged unless acted upon by gravity or another force. There is no natural slowing. There is also no natural speeding up. The fastest humans have ever traveled relative to Earth occurred during Apollo missions returning from the Moon. As the spacecraft fell back into Earth's gravity well, it reached speeds of nearly 11 kilometers per second before atmospheric braking. This was brief and unrepeatable without similar conditions. Relative to the Sun, however, human speed records remain far lower than those of robotic probes. Crewed missions have stayed close to Earth, within the Moon's orbit. This is not due to a lack of courage, but to the immense complexity of keeping humans alive in deep space. As you sit with these facts, speed begins to feel less like a number and more like a boundary. It is constrained by energy density, engine efficiency, structural strength, and biological tolerance. Each constraint is measured independently, and all converge on similar limits. The rocket equation formalizes this relationship. It links the change in velocity a rocket can achieve to the exhaust velocity of its propellant and the ratio of its initial mass to final mass. The equation shows that adding fuel produces diminishing returns. To gain a little more speed, you must add disproportionately more mass, which itself requires more fuel. This is not a design flaw. It is a mathematical description of conservation of momentum. Engineers cannot bypass it. They can only work within it. You may notice that discussions of future propulsion often mention higher exhaust velocities. This is because exhaust velocity directly influences achievable speed. Chemical rockets have exhaust velocities limited by chemical bond energies. These limits are well measured in laboratories and engines. As long as propulsion relies on chemistry, maximum speeds will remain within a narrow range. Gravity assists can help, but only when planets are positioned correctly. Even then, gains are finite. When you compare these realities to the speed of light, the difference is profound. Light travels at 300,000 kilometers per second. The fastest spacecraft move at less than 1/10,000th of that speed. This ratio is not symbolic. It defines what distances are reachable within human time. At current maximum speeds, Reaching the outer boundary of the sun's influence takes decades. Reaching the nearest star would take tens of thousands of years. These numbers remain unchanged no matter how often they are recalculated, because they arise from measured velocities and measured distances. Understanding how fast humans can actually travel brings clarity. It replaces vague hope with precise expectation. Speed becomes something you can hold gently in your mind, tied to engines, trajectories, and physical limits rather than imagination. Within this clarity, space travel becomes quieter. There is no rush, no sudden leap across the stars. There is only steady motion through an immense environment, guided by gravity and constrained by energy. As your thoughts slow, you may notice a subtle shift. Speed no longer feels like the key question. Instead, endurance, resources, and time quietly begin to matter more, shaping how far motion can be sustained before the journey itself becomes the dominant challenge. You begin by focusing on something concrete and mechanical, a rocket engine. At its core, a chemical rocket is a device that converts stored chemical energy into motion. Fuel and oxidizer combine in a controlled reaction, producing hot gases that rush out through a nozzle. As those gases are expelled backward, the rocket moves forward. This motion follows a basic physical principle that governs all movement in the universe: conservation of momentum. Momentum is the product of mass and velocity. When mass is thrown in one direction, an equal and opposite momentum must appear elsewhere. In a rocket, the expelled exhaust carries momentum away, and the rocket gains momentum in the opposite direction. This is not a suggestion or an approximation. It is a rule confirmed in laboratories, firing tests, and every successful launch. The efficiency of a rocket engine depends largely on how fast it can expel exhaust. This speed is known as exhaust velocity. For chemical rockets, exhaust velocity is limited by the energy released when chemical bonds break and reform. No matter how refined the engine design becomes, the energy available is bounded by chemistry itself. The atoms involved can only release so much energy per unit mass. Typical chemical rockets achieve exhaust velocities of around 4 to 5 kilometers per second. This number varies slightly depending on fuel type and nozzle design, but it remains within a narrow range. Engineers have explored countless combinations, yet the limits remain consistent. The bonds between atoms define the ceiling. From this exhaust velocity emerges a crucial relationship between fuel and speed. As a rocket accelerates, it must carry fuel not only for propulsion, but also to accelerate the fuel it has not yet burned. Each additional kilogram of propellant adds mass that must itself be pushed. This compounding effect leads to diminishing returns. The mathematical description of this relationship is known as the rocket equation. While the equation itself is compact, its implications are profound. It shows that the maximum change in velocity a rocket can achieve depends on exhaust velocity and the ratio between its starting mass and final mass. To gain more speed, you must increase that ratio, often dramatically. In practical terms, this means that adding more fuel yields smaller and smaller gains in speed. Doubling fuel does not double velocity. Instead, the rocket grows heavier, requiring even more fuel to lift that fuel. This feedback loop quickly becomes unmanageable. You can see this reality in the structure of launch vehicles. Most rockets are composed almost entirely of propellant. The payload, whether a satellite or a crew capsule, represents only a tiny fraction of the total mass. Even the rocket itself, engines and structure included, is dwarfed by the fuel it carries. This design is not wasteful. It is necessary. Without that mass of propellant, the rocket would not reach orbit at all. The margins are thin, calculated carefully using physics that has been verified over centuries. Once a rocket reaches orbit, its situation changes. It no longer fights Earth's gravity directly. Yet the rocket equation still applies. Any further increase in speed requires burning more fuel, which must have been carried all along. This is why deep space missions are planned with extreme care, minimizing engine burns and relying on coasting whenever possible. Chemical rockets excel at providing large amounts of thrust over short durations. They are ideal for launch and rapid maneuvers. What they cannot do efficiently is provide sustained acceleration over long periods. Their fuel is consumed too quickly, and their exhaust velocity is too low to support prolonged thrust without enormous mass. This limitation becomes especially clear when considering interplanetary travel. To significantly reduce travel time, a spacecraft would need to accelerate for weeks or months. Chemical rockets cannot support this. They burn for minutes, sometimes seconds, then fall silent. You may wonder whether staging offers a solution. Staging does help. By discarding empty fuel tanks and engines, a rocket sheds mass, improving efficiency. This technique is why rockets appear as stacks rather than single vehicles. Yet staging does not remove the underlying limit. It only allows engineers to approach it more closely. Even with multiple stages, the total achievable speed remains constrained. Each stage obeys the same physics. Each gains velocity at the cost of expelling mass. The sum of these gains cannot exceed what the exhaust velocity and mass ratios allow. Another factor quietly shaping these limits is structural strength. Tanks must withstand internal pressure. Engines must endure extreme temperatures. Increasing performance often increases stress. Material science can improve margins, but cannot eliminate physical constraints. Energy density also matters. Chemical propellants store energy in molecular bonds. Compared to nuclear reactions, this energy density is low. This is not a flaw of current technology, but a property of matter itself. Breaking and forming chemical bonds releases millions of times less energy than altering atomic nuclei. This difference explains why chemical rockets plateau where they do. No amount of engineering ingenuity can extract nuclear-scale energy from chemical reactions. The ceiling is built into the physics. You see the consequences of this ceiling in mission timelines. Reaching Mars takes months, not days. Reaching the outer planets takes years. These durations are not arbitrary. They arise from trajectories optimized to minimize fuel use while respecting the rocket equation. Engineers choose transfer orbits that balance speed and efficiency. The most common interplanetary path is the Hohmann transfer, a gentle arc that uses minimal energy but requires patience. Faster trajectories exist, but their fuel demands grow rapidly, often beyond what chemical rockets can supply. Human missions are especially sensitive to these trade-offs. Carrying life support systems, shielding, and supplies increases mass. Increased mass reduces available speed. Every kilogram added to support survival subtracts from propulsion capability. This interplay forces careful compromises. Missions are designed not to maximize speed, but to maximize feasibility. The rocket equation acts as a quiet accountant, tallying mass, fuel, and velocity without emotion or flexibility. As you consider these constraints, it becomes clear that chemical rockets are not inadequate. They are simply well understood. Their limits are known, measured, and respected. They have carried humans to orbit, to the moon, and robotic explorers across the solar system. They perform exactly as physics predicts. The true limitation lies not in engineering creativity, but in the fundamental relationship between energy, mass, and momentum. To go faster for longer, a propulsion system must expel mass at much higher speeds or use a different energy source. Chemistry cannot provide that. This realization reshapes expectations. Chemical rockets are powerful tools for leaving Earth and navigating nearby space. They are not gateways to distant stars within a lifetime. Their role is defined by what they do best: short, intense bursts of acceleration. When you release the idea that more fuel automatically means more speed, space travel begins to feel more precise and grounded. Progress is measured in careful increments rather than dramatic leaps. Each mission becomes an exercise in optimization rather than ambition alone. As your thoughts settle, the limits of chemical propulsion feel less like barriers and more like boundaries that give shape to exploration. Within those boundaries, remarkable journeys remain possible. Beyond them, different approaches are required, shaped by different physical principles. In the quiet recognition of these limits, attention naturally drifts toward the less obvious constraints that emerge once propulsion is no longer the only concern, where sustaining motion becomes inseparable from sustaining life itself. You begin by noticing your breath. It happens without effort, quietly supplying oxygen to your blood and removing carbon dioxide with each exhale. On Earth, this process feels automatic because the environment constantly supports it. The atmosphere provides oxygen at the right pressure, plants and oceans help regulate its composition, and gravity keeps air evenly distributed. In space, none of this exists naturally. Every breath must be engineered. Life support is not a single system but a network of interdependent processes that replace what Earth normally provides for free. Oxygen must be generated or stored. Carbon dioxide must be removed. Water must be supplied, purified, and reused. Temperature must be controlled. Waste must be managed. Radiation must be reduced. Each requirement adds mass, complexity, and energy demand. Together, they quietly shape the true limits of travel distance. Oxygen is the most immediate need. A human consumes roughly 800 grams of oxygen per day. Without replacement, loss of consciousness occurs within seconds, and survival becomes impossible within minutes. Early spacecraft carried compressed oxygen tanks, a simple but finite solution. For short missions, this approach works. For longer journeys, stored oxygen quickly becomes impractical due to mass. Modern spacecraft rely on oxygen generation systems. These systems split water molecules into hydrogen and oxygen using electricity, a process called electrolysis. The oxygen is released into the cabin, while hydrogen is either vented or reused in other reactions. This technology is not experimental. It has operated aboard space stations for years, monitored continuously by sensors and maintenance crews. Carbon dioxide removal is equally critical. Exhaled carbon dioxide becomes toxic at relatively low concentrations. Chemical scrubbers, often using compounds like lithium hydroxide or regenerative systems with molecular sieves, remove carbon dioxide from the air. These systems require power, periodic maintenance, and sometimes replacement materials. Failure leads to rising carbon dioxide levels, affecting cognition and eventually survival. Water presents a more complex challenge. A human needs water for drinking, food preparation, and hygiene. Carrying all required water for a long mission quickly becomes impossible due to mass. This drives the need for recycling. On space stations, water is reclaimed from humidity, urine, and wastewater through multi-stage filtration and distillation. These systems achieve recovery rates above 90%, but never 100%. Every percentage point of loss accumulates over time. Over months or years, even small inefficiencies demand resupply or larger initial stores. Filters clog. Pumps wear down. Microbial growth must be controlled. Each solution introduces new failure modes that must be anticipated and mitigated. Food adds another layer. Unlike oxygen and water, food cannot yet be fully recycled. Calories must be stored, grown, or produced on board. Stored food degrades over time due to radiation exposure, oxidation, and microbial risks. Nutritional balance must be maintained to prevent deficiencies that weaken the immune system and bones. Experiments with growing plants in space have shown promise. Plants can produce oxygen, recycle carbon dioxide, and provide fresh food. However, plant growth requires light, water, nutrients, and space. Crop yields must be reliable and predictable. Failures cannot be easily corrected millions of kilometers from Earth. At present, plant systems supplement stored food rather than replace it entirely. Temperature control is another quiet requirement. Space itself is not cold or hot in the way air feels on Earth. Instead, temperature depends on radiation balance. Without atmosphere, heat does not dissipate through convection. Spacecraft must manage heat through insulation, radiators, and controlled circulation. Electronics, life support equipment, and human bodies all generate heat that must be removed to prevent overheating. Thermal control systems add mass and complexity. Radiators must be oriented correctly. Fluids must circulate reliably. Damage from micrometeoroids or degradation over time can impair heat rejection. These systems operate continuously, often unnoticed, yet they are essential to survival. Radiation exposure represents one of the most limiting factors for long-distance travel. Earth's magnetic field and atmosphere block most high-energy particles from the sun and deep space. Beyond low Earth orbit, this protection weakens dramatically. Astronauts are exposed to solar radiation and galactic cosmic rays, particles traveling near the speed of light. Radiation damages DNA, increases cancer risk, and affects the central nervous system. Shielding reduces exposure, but shielding adds mass. Dense materials are effective but heavy. Water provides some protection, which creates opportunities to integrate shielding with life support storage, but this only partially mitigates the problem. Measurements from spacecraft and lunar missions provide clear data. Radiation levels during interplanetary travel are significantly higher than in Earth orbit. Over months or years, cumulative doses approach or exceed current safety limits. This places a hard boundary on how long humans can remain in deep space without advanced protection. Gravity, or the lack of it, also affects life support indirectly. In microgravity, fluids shift within the body. Bones lose density. Muscles weaken. The cardiovascular system adapts in ways that become harmful over time. Countermeasures include exercise equipment and carefully designed routines, but these do not fully prevent degradation. Exercise devices take space and consume power. Crew time must be allocated. Even with strict regimens, astronauts lose bone density at rates that raise concern for missions lasting years. Medical data from long-duration spaceflight consistently confirms this trend. Psychological support is another often overlooked requirement. Humans are social, sensory beings. Isolation, confinement, and distance from Earth affect mental health. Space agencies study these effects through analog environments and long missions. Depression, anxiety, and cognitive changes are real risks that must be addressed through design, communication, and routine. Communication delay itself becomes a factor as distance increases. At Mars, signals take several minutes to travel each way. Real-time conversation becomes impossible. Emergency support from Earth is delayed. Crew autonomy must increase, placing greater cognitive and emotional demands on individuals. All these systems interact. Power generation must support oxygen production, water recycling, temperature control, lighting, communication, and medical equipment. Power failures cascade quickly. Redundancy becomes essential, adding further mass and complexity. Solar panels provide reliable power near Earth, but their effectiveness decreases with distance from the sun. Nuclear power offers alternatives, but introduces new challenges related to safety, heat management, and political constraints. Each power choice influences life support capabilities. Maintenance becomes a central concern. Machines fail. Components wear out. Filters clog. Valves stick. On Earth, replacement and repair are straightforward. In deep space, every spare part must be carried. Predicting failures years in advance is extremely difficult, even with extensive testing. The longer the journey, the more supplies and redundancy are required. This creates a feedback loop. More life support demands more mass. More mass demands more propulsion capability. More propulsion demands more fuel. Each layer tightens the constraints. Historical missions provide clear evidence. The International Space Station represents the most advanced life support system ever built. It requires constant resupply, maintenance, and monitoring. It operates only a few hundred kilometers above Earth, where emergency return is possible within hours. Scaling this system to operate independently for years, far from Earth, is an engineering challenge of unprecedented difficulty. Research continues, but current capabilities remain limited. No closed-loop system has yet supported humans indefinitely without external input. As you reflect on these realities, distance begins to feel less abstract. It becomes something measured not only in kilometers or years, but in breaths, meals, heartbeats, and cellular repairs. The human body is not designed for space, and technology must compensate continuously. This compensation is possible within certain bounds. Short missions, orbital stays, and journeys to nearby destinations fit within what life support systems can currently sustain. Beyond that, the challenges grow rapidly, not gradually. Understanding this does not diminish the achievement of spaceflight. It deepens appreciation for its precision. Every successful mission represents thousands of systems working together to maintain a narrow window of habitability inside an otherwise hostile environment. As your awareness settles into this perspective, travel through space feels less like motion through emptiness and more like carrying a fragile pocket of Earth along a carefully calculated path. The question of how far one can go becomes inseparable from how long that pocket can remain stable, balanced, and alive under conditions that never pause or soften. You begin by placing yourself at a familiar starting point. Earth. It is not just a planet, but a moving platform already traveling through space. Earth orbits the Sun at roughly 30 kilometers per second, carrying everything on its surface along with it. From this moving vantage point, every journey into the solar system begins with inherited motion, shaped by gravity and momentum rather than intention. The solar system itself is not arranged like a map with evenly spaced destinations. Distances change constantly as planets follow elliptical orbits governed by gravity. Sometimes worlds draw closer together, sometimes they drift farther apart. These motions are predictable, calculated centuries in advance using physical laws confirmed through observation. The Moon is the nearest destination. At an average distance of 384,000 kilometers, it is close enough that travel times are measured in days rather than months. Human missions have crossed this distance repeatedly, guided by trajectories that balance speed and fuel efficiency. The journey fits comfortably within human perception of time, allowing crews to remain alert, functional, and supported throughout. Beyond the Moon, distances expand rapidly. Mars, often described as a neighboring world, orbits at an average distance of about 1.5 astronomical units from the Sun depending on orbital alignment. The distance between Earth and Mars ranges from roughly 56 million to over 400 million kilometers. These variations dictate launch windows that open approximately every 26 months. Travel to Mars using current propulsion typically takes 6 to 9 months. This duration is not arbitrary. It reflects trajectories that minimize fuel use while remaining within the limits of chemical rockets. Faster paths exist, but their energy demands rise steeply. The chosen routes are compromises shaped by physics rather than preference. During this time, crews remain fully dependent on life support systems. Supplies must be carefully calculated. Radiation exposure accumulates. Communication delays increase from seconds to several minutes. Mars remains reachable, but only through sustained technological support and careful planning. Asteroids occupy another region of the solar system that feels both near and distant. Many near-Earth asteroids pass closer than Mars, some even closer than the Moon. These objects travel along predictable orbits, tracked continuously by telescopes. In principle, they are reachable with modest changes in velocity, making them interesting targets for exploration. Missions to asteroids highlight an important distinction. Distance alone does not define reachability. Orbital energy matters more. Some asteroids require less fuel to reach than the Moon, despite being farther away at times. This counterintuitive reality arises from how orbits intersect and how velocity changes are applied. The asteroid belt lies farther out, between Mars and Jupiter. It spans a broad region rather than a single location. Reaching it requires years of travel, depending on trajectory and destination. Robotic missions have visited this region, providing detailed data about composition and structure. For humans, such journeys remain challenging but not fundamentally impossible within a lifetime. Jupiter marks a significant boundary. It is massive, distant, and surrounded by intense radiation belts. Travel times to Jupiter using chemical propulsion typically exceed 5 years. The environment near the planet exposes crews to radiation levels far higher than those near Earth or Mars. Shielding requirements increase dramatically. Saturn lies farther still, about 9.5 astronomical units from the Sun. Robotic missions take 7 to 10 years to arrive. For humans, such a journey would consume a large fraction of a lifetime when including travel, exploration, and return. Life support and radiation challenges multiply over such durations. Beyond Saturn, the solar system stretches outward into regions rarely discussed in human terms. Uranus and Neptune orbit at distances where sunlight is weak and travel times span decades. Reaching them within one lifetime using current technology is theoretically possible for robotic probes, but deeply impractical for humans. The Kuiper belt extends even farther, a vast population of icy bodies beyond Neptune. Objects here orbit slowly, completing a single revolution around the Sun in centuries. New Horizons reached Pluto after nearly 10 years of travel, moving at extraordinary speed for a spacecraft. Even then, the encounter was brief, a flyby rather than a stay. These examples illustrate a quiet pattern. The solar system is reachable in pieces, not as a whole. Inner regions fall within human timeframes. Outer regions stretch beyond them. The dividing line is not sharp, but it is consistent across mission analyses. Orbital mechanics play a central role in shaping this reachability. Spacecraft do not travel in straight lines toward their targets. They follow curved paths dictated by gravity, often looping around planets to gain or lose energy. These paths are calculated precisely, using equations refined through centuries of observation. Fuel efficiency often matters more than speed. Missions are designed to use gravity as an ally, allowing spacecraft to change velocity without burning propellant. This technique extends reach but increases travel time. For humans, time spent in transit carries biological and psychological costs. Robotic probes tolerate these costs differently. They do not require air, water, or protection from radiation. They do not age. They can travel slowly for decades without concern. This difference explains why robotic exploration extends far beyond where humans have gone or are likely to go soon. Within a human lifetime, meaningful exploration clusters closer to the Sun-Earth orbit, the Moon, Mars, and select near-Earth objects form a region where travel durations remain compatible with biological limits. These destinations are separated by millions of kilometers, yet still belong to the same neighborhood in human terms. This neighborhood is dynamic rather than static. Launch opportunities depend on alignment. Travel times vary. Each mission must adapt to celestial motion. Space is not empty, but structured by gravity, mass, and time. Understanding the solar system this way changes perspective. It is no longer a distant abstraction filled with unreachable worlds. It becomes a place with pathways, constraints, and rhythms. Some routes are short and familiar. Others are long and demanding. The idea of reachability is not about ambition alone. It is about matching technological capability with human endurance. The solar system offers destinations that fit within this balance, and others that do not. As you settle into this understanding, distance begins to feel layered rather than overwhelming. The inner solar system emerges as a region where human presence is possible, though never effortless. Farther out, travel becomes increasingly symbolic, carried out by instruments rather than bodies. In this quiet framing, the solar system feels less like an endless expanse and more like a carefully measured environment, where motion is slow, deliberate, and governed by rules that reward patience over speed and preparation over impulse. You begin by noticing how time feels inside your body. Your heart beats at a steady rhythm. Your breath follows a gentle pattern. Sleep arrives and recedes in cycles shaped by light and darkness. On Earth, these rhythms are reinforced constantly by gravity, day and night, and the subtle cues of a living environment. In space, many of these cues weaken or disappear, and time begins to express itself in unfamiliar ways. A long voyage through space does not only move you across distance. It moves you through prolonged exposure to conditions your body did not evolve to experience. Microgravity, radiation, isolation, and confinement all unfold slowly, accumulating effects that are often invisible at first. The problem of time arises not because days pass, but because biology changes as they do. Microgravity is one of the most studied influences on long-duration spaceflight. When gravity no longer pulls fluids downward, they redistribute throughout the body. Blood and other fluids shift toward the head and chest, increasing pressure in the upper body while reducing it in the legs. Astronauts often experience facial swelling and reduced leg volume as a direct result of this redistribution. Over weeks and months, the absence of gravity alters how bones and muscles behave. On Earth, Bones constantly remodel themselves in response to load. Gravity and movement stimulate bone cells to maintain density and strength. In microgravity, this stimulation weakens. Bone tissue breaks down faster than it rebuilds, leading to measurable density loss. This loss is not uniform. Weight-bearing bones, such as those in the hips and spine, are most affected. Studies of astronauts returning from long missions consistently show bone density decreases of 1 to 2% per month in these areas. Recovery on Earth is possible, but not always complete. Time spent without gravity leaves a lasting imprint. Muscles follow a similar pattern. Without the need to support body weight, muscles weaken and shrink. This process, known as atrophy, affects posture, movement, and endurance. Exercise countermeasures slow the decline, but do not fully prevent it. Hours each day are devoted to resistance and aerobic training, using specially designed equipment to simulate load. The cardiovascular system also adapts. In microgravity, the heart does not need to work as hard to pump blood upward. Over time, heart muscle mass can decrease slightly. Upon return to gravity, this adaptation can cause dizziness or fainting, as the body struggles to readjust to familiar forces. These changes unfold gradually. A short mission may produce mild, reversible effects. A mission lasting many months introduces deeper adaptations. Time becomes a multiplier, amplifying each biological response. Radiation exposure accumulates in a similar way. Outside Earth's protective magnetic field, high-energy particles pass through spacecraft walls and human tissue. Each particle interaction carries a small risk of damaging DNA. Over time, these risks add together, increasing the likelihood of cancer and other health effects. Measurements from space missions provide clear data. Radiation doses during 6-month stays aboard space stations are significantly higher than those experienced on Earth. During interplanetary travel, doses rise further due to reduced shielding from Earth's magnetic field. No safe threshold exists below which radiation has zero effect. Risk scales with time. Time also influences vision. Many astronauts experience changes in eyesight during and after long missions. Increased pressure within the skull, linked to fluid shifts, can alter the shape of the eyeball and optic nerve. This condition has been documented repeatedly and remains an active area of research. Sleep, another biological cornerstone, becomes more difficult to regulate. Without a natural day-night cycle, circadian rhythms weaken. Artificial lighting helps, but cannot perfectly replicate Earth's cues. Sleep quality often declines, affecting mood, attention, and decision-making. Psychological effects unfold alongside physical ones. Humans evolved in rich sensory environments filled with variation, social interaction, and natural stimuli. Spacecraft interiors are confined, repetitive, and isolated. Over time, monotony and confinement can strain emotional resilience. Studies conducted in space analog environments, such as Antarctic research stations and sealed habitats, reveal patterns. Individuals may experience mood fluctuations, reduced motivation, and changes in interpersonal dynamics. These effects vary widely between people, but time remains a consistent factor. Distance from Earth compounds these challenges. As communication delays increase, conversations become asynchronous. Immediate reassurance and guidance fade. Crews must rely more on themselves, making decisions with limited external input. This autonomy is empowering, but also demanding. Time also shapes how systems age. Machines, like bodies, experience wear. Pumps degrade. Filters clog. Electronics suffer from radiation-induced faults. The longer a mission lasts, the higher the probability that something will fail. Redundancy mitigates risk, but never eliminates it. Maintenance requires tools, spare parts, and expertise. Carrying replacements increases mass. Anticipating every possible failure is nearly impossible. Engineers rely on statistics and testing, yet uncertainty grows with time. Food storage illustrates another temporal challenge. Even carefully packaged food degrades. Vitamins break down. Texture and flavor change. Over months or years, nutritional quality declines unless supplemented by fresh sources. Appetite can suffer, further affecting health. Time also influences exposure to isolation. Separation from Earth is not only physical, but temporal. News arrives late. Events unfold without immediate awareness. This separation can produce a sense of disconnection that deepens as distance grows. A long voyage becomes a sustained experiment in adaptation. The human body and mind adjust continuously, seeking new equilibria under unfamiliar conditions. Some adaptations are beneficial in the short term, but problematic in the long term. Aging itself does not pause in space. Cellular processes continue. DNA accumulates damage. Telomeres, protective caps on chromosomes, change length in response to stress and environment. Studies of astronauts show complex biological responses, some reversible, others less so. Time spent traveling cannot be reclaimed. Months in transit are months not spent exploring, building, or returning. For a human lifetime, this opportunity cost matters. A journey that consumes years must justify its duration against what can be accomplished during it. When travel durations stretch into decades, the question shifts. It is no longer about reaching a destination, but about living the journey itself. Human lives are finite. Memory, learning, and purpose are shaped by time experienced, not distance covered. Robotic probes face none of these constraints. They do not age biologically. They do not require sleep or emotional support. Their time horizon extends far beyond a human lifespan. This difference explains why robotic exploration reaches regions humans cannot realistically visit. Understanding the problem of time reframes space travel. Speed alone cannot solve it. Faster propulsion helps, but only within limits. Biological processes do not accelerate safely beyond certain thresholds. Life unfolds at its own pace. As you reflect on these realities, time becomes tangible. It is felt in bone density charts, radiation dosimeters, sleep logs, and maintenance schedules. It presses gently but persistently on every system involved in travel. Long voyages are not impossible, but they are transformative. They change bodies, minds, and machines in measurable ways. Each added month deepens those changes. In this quiet awareness, distance feels secondary. The central question becomes how long stability can be maintained, how long adaptation remains healthy, and how long purpose can be sustained without erosion. As this perspective settles, attention naturally shifts toward the technologies that attempt to shorten time's influence, not by ignoring it, but by working within physics to reshape how motion and duration interact. You begin by returning to the idea of energy, not as an abstract quantity, but as something stored in matter itself. Chemical rockets rely on energy locked in molecular bonds, released when atoms rearrange. Nuclear propulsion turns to a deeper source, one that resides within atomic nuclei. This difference is not subtle. It is measured, quantified, and demonstrated repeatedly in both laboratories and reactors. Inside an atomic nucleus, forces bind protons and neutrons together with immense strength. When those bonds are altered through fission or fusion, the energy released per unit mass far exceeds anything chemistry can provide. This is not speculative. It is the same physics that powers nuclear reactors and has been studied for decades. The question is not whether nuclear energy exists, but how it can be applied to propulsion in controlled, reliable ways. One approach is nuclear thermal propulsion. In this system, a nuclear reactor replaces chemical combustion as the heat source. Instead of burning fuel, the reactor heats a propellant, usually hydrogen, to extremely high temperatures. The hot hydrogen expands and rushes out through a nozzle, producing thrust. The motion still obeys conservation of momentum, but the exhaust velocity is much higher. Hydrogen is chosen because it is light. For a given amount of thermal energy, lighter particles achieve higher speeds. Nuclear thermal engines can theoretically achieve exhaust velocities around 8 to 9 kilometers per second, roughly double that of chemical rockets. This increase is not incremental. It has profound implications for achievable speed. Doubling exhaust velocity does not merely double performance. Through the rocket equation, it allows much larger changes in velocity for the same mass ratio. Missions that would be marginal or impossible with chemical propulsion become feasible. travel times shorten, payload fractions improve. These engines are not imaginary. Nuclear thermal propulsion was tested extensively during the mid-20th century. Ground tests demonstrated stable operation, predictable thrust, and high efficiency. The physics worked exactly as expected. Development slowed for political and logistical reasons rather than scientific ones. Another approach is nuclear electric propulsion. Here, a nuclear reactor generates electricity, which powers electric thrusters such as ion engines. These thrusters accelerate charged particles using electromagnetic fields, achieving exhaust velocities far higher than any chemical or thermal engine, sometimes tens of kilometers per second. The trade-off is thrust. Electric propulsion produces very small forces, often measured in fractions of a newton. Acceleration is gentle, almost imperceptible. Over long periods, however, this continuous acceleration can build substantial speed. Ion engines have flown successfully on multiple missions. They are efficient, reliable, and well understood. With nuclear power instead of solar panels, they could operate far from the sun, where sunlight weakens. This combination offers steady propulsion over months or years. These systems change how speed is accumulated. Instead of brief bursts followed by coasting, a spacecraft could accelerate gradually for extended durations. Over time, total velocity change could exceed what chemical rockets provide, even if instantaneous thrust remains low. For robotic missions, this approach is transformative. For human missions, the picture is more complex. Continuous acceleration, even at low levels, must remain within biological tolerance. Power systems must be shielded. Heat must be managed. Radiation from the reactor itself becomes an additional concern. Nuclear propulsion does not eliminate mass constraints. Reactors, shielding, radiators, and power conversion systems add significant weight. Hydrogen tanks for nuclear thermal engines must store propellant at low density. Electric systems require large radiators to shed waste heat. The balance between increased exhaust velocity and added system mass determines net benefit. Engineers analyze this carefully using models validated against real hardware. In many scenarios, nuclear propulsion offers clear advantages. In others, gains are modest. Travel times to Mars provide a useful reference. Nuclear thermal propulsion could reduce transit durations from 6 to 9 months down to 3 or 4. This reduction matters. Shorter travel means lower radiation exposure, reduced life support demands, and less cumulative biological stress. Yet even with these improvements, Mars remains months away, not weeks. Nuclear propulsion shifts boundaries but does not erase them. The solar system becomes more accessible, but still vast. For missions beyond Mars, benefits continue. Nuclear systems allow greater flexibility in launch windows, reducing dependence on precise orbital alignment. They support heavier payloads and more robust shielding. Outer planet missions become more plausible within a lifetime. Still, travel to Jupiter or Saturn would consume years. Radiation belts near Jupiter pose severe challenges. Nuclear propulsion cannot remove those hazards. It can only shorten the time spent approaching and departing. Interstellar distances remain essentially unchanged in human terms. Even at exhaust velocities far beyond chemical limits, achievable spacecraft speeds remain a tiny fraction of the speed of light. Reaching nearby stars would still require thousands of years. Relativistic effects remain negligible at these speeds. Time dilation does not meaningfully reduce travel time experienced by crews. Physics remains consistent and unyielding. Another consideration is reliability over time. Nuclear reactors must operate safely for years without maintenance. Control systems must withstand radiation damage. Fuel elements must remain stable under thermal cycling. These challenges are solvable in principle, but demand extensive testing. Public and political factors also shape feasibility. Launching nuclear material from Earth carries risk. Safety systems must ensure containment under worst-case scenarios. These concerns are addressed through engineering and regulation, but they add complexity. Despite these challenges, nuclear propulsion represents the most mature path toward faster human travel within the solar system. It is grounded in tested physics, supported by experimental data, and constrained by known limits rather than unknown ones. Understanding what nuclear propulsion changes requires recognizing what it does not. It does not free humans from life support needs. It does not eliminate radiation exposure. It does not allow arbitrary speed increases. It simply shifts the balance. Time remains central. Faster travel reduces exposure, but does not eliminate cumulative effects. Biology still adapts over months and years. Machines still age. Supplies still degrade. The human experience of a journey remains shaped by duration. Shortening a voyage by half can make the difference between manageable and dangerous. Shortening it further becomes increasingly difficult. As you hold this perspective, nuclear propulsion feels neither miraculous nor disappointing. It is a powerful tool that works exactly as physics predicts. It expands reach within a well-defined region, making some journeys safer and more practical. The solar system becomes more navigable, not smaller. Distances remain immense, but time required to cross them shifts downward in measurable ways. In this quiet understanding, attention naturally turns toward how motion through space interacts with the flow of time itself, and why even dramatic improvements in propulsion do not allow time to be bypassed, only managed within the same unchanging physical framework. You begin with time as you experience it. Seconds pass steadily. Minutes gather into hours. Your body senses time through heartbeat, breath, hunger, and fatigue. This experience feels universal and constant, yet careful measurement reveals that time does not flow identically everywhere. It responds to motion, gravity, and energy in ways that have been confirmed repeatedly through observation and experiment. Relativity begins with a simple but precise statement. The laws of physics are the same for all observers moving at constant speed, and the speed of light in a vacuum is the same for everyone regardless of motion. These principles were proposed to resolve inconsistencies in measured light behavior, and they have since been tested to extraordinary precision. From these principles follows an unexpected result. Time does not pass at the same rate for all observers. When an object moves very fast relative to another, time for that object passes more slowly compared to a stationary observer. This effect is called time dilation. It is not a psychological illusion. It is a measurable change in elapsed time recorded by clocks. Experiments confirm this repeatedly. Atomic clocks flown aboard aircraft tick slightly more slowly than identical clocks left on the ground. Satellites orbiting Earth must correct for time dilation effects to maintain accurate positioning. These corrections are essential, not optional. Without them, navigation systems would drift by kilometers each day. Time dilation depends on speed. The faster an object moves, the greater the effect. At everyday speeds, the difference is far too small to notice. At speeds approaching the speed of light, the effect becomes significant. This relationship is described mathematically and verified through particle accelerators, where unstable particles live longer when moving at high velocities. Gravity also affects time. According to general relativity, clocks closer to a massive object tick more slowly than clocks farther away. This effect has been measured using precise clocks placed at different altitudes on Earth. Even a difference of a few meters produces a measurable change. Gravity shapes time as surely as it shapes motion. For space travel, these effects matter in principle. A spacecraft moving very fast will experience time differently from Earth. A clock aboard the spacecraft will lag behind a clock on the ground. Yet the magnitude of this difference depends on speed. At the fastest speeds humans have achieved, time dilation is extremely small. Even at 17 kilometers per second, the speed of the fastest probes, the effect amounts to fractions of a second over decades. For human missions, this difference is biologically meaningless. Aging proceeds almost identically. This reality often surprises people because relativity is frequently associated with dramatic time effects. Those effects are real, but only at speeds far beyond current or foreseeable human travel. Reaching such speeds requires energy that scales steeply with velocity. As speed increases, energy requirements grow without bound. Chemical and nuclear propulsion cannot approach these regimes. Even advanced concepts produce velocities that remain tiny fractions of light speed. At 10% of light speed, time dilation becomes noticeable. At 1%, it is still modest. Human spacecraft operate orders of magnitude below even that. Gravity-induced time dilation during space travel is also limited. While orbiting Earth, astronauts experience slightly faster time passage than people on the surface because they are farther from Earth's mass. This effect partially offsets velocity-based dilation. The net difference remains small. These facts ground relativity firmly in measurement rather than imagination. Time dilation is real, but it does not offer a shortcut across space for humans. It does not compress lifetimes or allow journeys to distant stars within a single lifespan. Human perception of time complicates this further. Even without relativistic effects, time can feel stretched or compressed. Long periods of isolation can make days blur together. Novel experiences can make time feel rich and expansive. Routine can make it feel brief. In space, altered light cycles, confinement, and workload affect time perception. Astronauts report that missions feel both long and short in retrospect. This subjective experience does not reflect physical time, but it influences how duration is lived. Physical time remains what clocks record. Biological time unfolds through cellular processes, aging, and metabolism. Relativity alters physical time under specific conditions, but biology responds to internal chemistry and environment. At human travel speeds, these remain aligned. This alignment matters. You cannot rely on relativistic effects to preserve youth or extend endurance. Your cells age according to chemical reactions that are largely unaffected by small changes in elapsed physical time. Relativity also reinforces the idea that space and time are not separate entities. They form a unified structure called spacetime. Motion through space affects motion through time. Gravity curves spacetime, guiding both. This framework helps explain why orbits behave as they do and why gravity assists work. Spacecraft follow paths shaped by spacetime curvature. These paths are predictable and measurable. Yet even within this elegant framework, constraints remain firm. No object with mass can reach or exceed the speed of light. This is not a technological limitation, but a structural feature of spacetime itself. Approaching light speed requires infinite energy. Because of this, there is no gradual path from current propulsion to near-light travel. Each increase in speed demands exponentially more energy. Nuclear propulsion improves efficiency, but does not alter this curve. Time dilation, therefore, remains a subtle effect for human travel. It must be accounted for in navigation and communication systems, but it does not redefine reachability. Understanding this brings calm clarity. Relativity does not undermine earlier conclusions about distance and duration. It reinforces them with deeper consistency. Your lifetime remains anchored to biological processes unfolding at nearly the same rate wherever you go within the solar system. Time spent traveling is time experienced fully, not compressed or skipped. As you rest with this understanding, space feels orderly rather than paradoxical. Time behaves differently under extreme conditions, but those conditions lie far beyond human reach. Within the realm humans can explore, time remains steady, patient, and unavoidable. In this quiet recognition, attention naturally returns to the vast distances between stars, where even the most generous relativistic effects fail to bring them within personal reach, leaving human experience bound once more to familiar scales of motion and endurance. You begin by letting go of the familiar boundaries of the solar system. The planets, asteroids, and distant icy bodies fade behind you, not because they disappear, but because the scale ahead grows so dramatically that everything before it begins to feel compact by comparison. Interstellar space is not defined by emptiness alone. It is defined by distance so large that motion through it must be measured differently. The nearest star system lies just beyond the outer edge of the Sun's influence. Proxima Centauri, a small red dwarf star, orbits as part of a three-star system known as Alpha Centauri. Its distance from Earth is about 4.2 light-years. This number is not symbolic. It comes from precise measurements of stellar parallax, the tiny apparent shift of a star's position as Earth moves around the Sun. A light-year is the distance light travels in 1 year at its constant speed in a vacuum. Light moves at about 300,000 kilometers per second. Over a year, that adds up to nearly 10 trillion kilometers. 4.2 light-years therefore represent more than 40 trillion kilometers. This distance is not exaggerated. It is measured repeatedly and independently using multiple methods. When you translate this distance into travel time using known spacecraft speeds, its scale becomes clearer. The fastest human-made objects move at around 17 kilometers per second relative to the Sun. At that speed, reaching Proxima Centauri would take roughly 75,000 years. This calculation assumes constant speed and no slowing, an optimistic simplification. 75,000 years is not an abstract figure. It represents 3,000 human generations. Entire civilizations rise and fall over far shorter spans. Languages transform, continents shift, climate cycles repeat. The human body, which evolves slowly over thousands of years, cannot personally experience such a journey. Even if propulsion technology improved significantly, the reduction would remain limited. Doubling speed halves travel time, but having 75,000 years still leaves tens of thousands. Increasing speed by an order of magnitude reduces the journey to several thousand years, still far beyond a lifetime. These numbers arise not from pessimism, but from straightforward division. Distance divided by speed produces time. No assumption changes that relationship unless speed changes dramatically. Interstellar distances grow quickly beyond the nearest stars. Many stars visible in the night sky lie tens, hundreds, or thousands of light-years away. The Milky Way galaxy itself spans about 100,000 light-years from edge to edge. Light from its far side began traveling toward Earth long before humans existed. When you look up at the sky, you are already seeing into the past. Starlight carries information across time as well as space. This fact is often described poetically, but it is fundamentally physical. Photons take time to travel, and that travel time preserves history. Human exploration, by contrast, is bound to presence. To explore personally means to arrive while alive, aware, and capable of interaction. Interstellar distances stretch far beyond what presence allows. Even advanced propulsion concepts do not change this in human terms. Nuclear propulsion improves efficiency, but achievable speeds remain small fractions of light speed. Electric propulsion accumulates velocity slowly, but cannot reach relativistic regimes within practical mass limits. Speculative ideas involving fusion propulsion promise higher exhaust velocities, yet controlled fusion itself remains an unsolved engineering challenge. Even optimistic projections place achievable spacecraft speeds at a few percent of light speed at best. At 5%, reaching Proxima Centauri would take more than 80 years, not counting acceleration and deceleration. 80 years matches the upper bound of a human lifetime, but only under idealized assumptions. The crew would spend nearly their entire life in transit with no margin for error. Radiation exposure over such a duration would far exceed known safety limits. Life support systems would need to operate flawlessly for decades. Acceleration itself becomes a problem. Reaching 5% of light speed safely requires years of continuous thrust at tolerable acceleration levels. Slowing down requires the same effort in reverse. The usable cruise phase shrinks. Energy requirements grow rapidly as speed increases. Relativistic mass-energy relationships demand more and more energy for smaller gains in velocity. This is not a technological hurdle waiting to be cleared. It is a property of spacetime confirmed through particle physics. Human perception often struggles with these scales because everyday experience provides no reference. On Earth, distances feel conquerable. Oceans were crossed in weeks once technology allowed. Aircraft reduced that to hours. It is tempting to extend this trend outward. Interstellar space resists that extension. The distances involved are not just larger. They are qualitatively different. They exceed what incremental improvements can bridge within a biological lifespan. This does not mean stars are unreachable in every sense. Robotic probes could, in principle, be sent on multi-thousand-year journeys. Messages can be transmitted at light speed. Observation allows detailed study without physical arrival. But personal presence remains constrained. A human traveler cannot meaningfully experience interstellar space as a destination in the same way planets can be experienced. The journey itself would dominate existence. Generation ships are often proposed as a response. These involve multiple generations living and dying aboard a vessel en route to another star. While grounded in basic physics, they shift the question. The original travelers would never arrive. The destination becomes meaningful only to descendants. Cryogenic preservation is another idea, but current science offers no method for safely suspending and restarting complex biological systems for decades. Medical hypothermia slows metabolism temporarily, but does not stop aging or prevent long-term damage. Relativity does not rescue the situation. Time dilation becomes significant only at speeds near light speed. Human propulsion remains far below that threshold. For a crew traveling at 5% of light speed, time dilation reduces perceived travel time by less than 1%. Interstellar distances therefore remain largely fixed in human context. They are not softened by perception, technology, or clever framing. They remain vast, silent, and persistent. This realization can feel stark, but it also brings clarity. The universe is not withholding access arbitrarily. It is structured according to consistent rules. Those rules apply everywhere without exception. Within these rules, the solar system emerges as a uniquely accessible region. Its scale aligns with human endurance when aided by technology. Beyond it, distances expand faster than capability. Understanding this boundary allows curiosity to settle rather than strain. You no longer need to imagine reaching everything personally. Observation, measurement, and inference become the primary tools. Astronomy itself thrives under this constraint. Telescopes collect light across wavelengths. Spectroscopy reveals composition. Motion is inferred from Doppler shifts. Planets are detected around other stars through minute changes in starlight. These methods allow intimate knowledge without travel. You can know a star's temperature, mass, age, and chemistry without ever approaching it. This knowledge is reliable, repeatable, and precise. Human exploration therefore splits naturally into two modes. Presence-based exploration occurs where time and distance permit survival. Observation-based exploration extends far beyond, limited only by light speed and instrumentation. Both modes are valuable. Neither diminishes the other. They simply operate on different scales. As you sit with interstellar distances framed this way, the universe feels quieter. There is no urgency to cross what cannot be crossed. There is instead an invitation to understand what can be reached, and to observe what cannot. The stars remain where they are, separated by immense intervals that preserve their individuality. Motion between them is rare and slow. Time stretches wide. In this stillness, the question of travel gives way to a deeper one about how humans choose to engage with a universe that offers both proximity and separation in precise, measurable balance, guiding attention back toward the forms of exploration that respect time as much as distance. You begin by returning to a simple constraint that has appeared again and again. A human life has a beginning and an end. No matter how advanced technology becomes, biological aging continues. Cells divide, repair mechanisms slowly weaken, and time moves forward without pause. When distances grow so large that travel would take longer than a lifetime, a different approach naturally emerges, one that does not attempt to compress time, but instead accepts it. A generation ship is not a faster spacecraft. It is a slower one, deliberately so. Its defining feature is not speed, but duration. The journey is planned to last many human lifetimes, long enough that the people who depart are not the people who arrive. Children are born, grow old, and die while the ship remains in motion, carrying a continuous human presence through space. This idea does not violate any known laws of physics. In fact, it aligns closely with them. At modest speeds, well below relativistic thresholds, a spacecraft could travel steadily for thousands of years without requiring impossible amounts of energy. The challenge shifts away from propulsion and toward survival, stability, and continuity. When you think about such a vessel, it helps to release familiar ideas about travel. There is no destination within personal reach. There is no arrival to anticipate. The journey itself becomes the environment in which life unfolds. Space travel stops being an event and becomes a condition. From an engineering perspective, the requirements are immense. A generation ship must function as a self-contained world. Air, water, food, waste recycling, temperature control, and radiation shielding must operate reliably for centuries or millennia. Every system must be maintainable by people who did not build it and who may not fully understand its original design. Closed-loop life support becomes essential. Losses that are tolerable over months become catastrophic over centuries. Even a 1% inefficiency compounds into depletion over long durations. Recycling systems must approach near-total recovery, and even then, small reserves must exist to buffer unexpected losses. Food production cannot rely on stored supplies. Agriculture must occur on board. Plants would need to grow under artificial light, in controlled environments, producing consistent yields year after year. Soil health, nutrient cycles, and genetic diversity all become critical concerns. Crop failures cannot be corrected through resupply. Water must circulate endlessly, purified and reused through multiple stages. Microbial contamination must be controlled. Infrastructure must be reparable using onboard materials. Every pipe, seal, and valve becomes part of a long-term ecological system rather than a temporary utility. Radiation exposure accumulates relentlessly over time. Shielding must be thick enough to reduce dose rates to levels compatible with lifelong exposure. This shielding adds mass which affects propulsion, but over long journeys, speed is less critical than protection. Dense materials, water layers, or regolith harvested from asteroids might be used to absorb high-energy particles. Gravity presents another challenge. Prolonged exposure to microgravity leads to irreversible health effects over generations. To address this, many designs incorporate rotation. By spinning the ship, centrifugal acceleration creates an artificial gravity environment along the outer rim. This concept is well understood physically and has been tested in smaller experimental setups. The rotation rate must be carefully chosen. Too fast and motion sickness occurs. Too slow and gravity remains weak. The structure must withstand continuous stress for centuries without catastrophic failure. Materials fatigue becomes a central concern. Beyond engineering, biology introduces deeper complexity. A closed population traveling for many generations faces genetic risks. Without sufficient genetic diversity, inherited disorders become more common. Careful population management would be required, including controlled reproduction and genetic screening. Such interventions raise ethical questions, but even without addressing ethics, the biological constraints remain. Population size must be large enough to avoid genetic bottlenecks, yet small enough to be supported by onboard resources. Studies suggest that thousands of individuals may be required for long-term genetic stability. Disease dynamics also change. In a closed environment, pathogens can persist indefinitely. Immune systems evolve in response to limited exposure. Medical knowledge must be preserved and applied consistently across generations, without access to external expertise. Psychological and cultural continuity becomes just as important as physical survival. Humans derive meaning from shared stories, goals, and identities. Over centuries, language evolves. Values shift. Knowledge can be lost if not actively maintained. Education becomes the primary mechanism of survival. Each generation must learn not only how to live, but how to maintain the systems that support life. Technical manuals alone are insufficient. Skills must be practiced, transmitted, and adapted to changing conditions. The original purpose of the journey may fade. Descendants may feel no connection to a distant star they will never personally see. The ship itself becomes home, not a vehicle. Motivation must shift from arrival to preservation. This transformation changes the nature of the mission. It is no longer about exploration in the traditional sense. It is about continuity of a lineage through space. The destination becomes symbolic rather than experiential. Time reshapes identity. For the people aboard, the stars outside remain distant and unchanged across generations. The interior environment becomes the entire world. Earth becomes a story, a memory passed down rather than a lived reality. From a physical standpoint, nothing prevents such a ship from traveling between stars. At modest speeds, tens of thousands of years could pass without requiring extreme propulsion. Interstellar distances become manageable when time is abundant. Yet abundance of time introduces fragility. The longer a system operates, the greater the chance of failure. Meteoroid impacts, material degradation, unforeseen interactions, and human error accumulate in probability. Redundancy helps, but redundancy itself adds complexity. Complex systems fail in complex ways. Predicting every possible failure over millennia is beyond current capability. There is also the question of arrival. Slowing down requires energy and planning. If the destination star system differs significantly from expectations, adaptation may be required upon arrival. The environment may not support immediate habitation. The people who arrive will not be the people who decided to go. Consent becomes abstract. Choice becomes historical rather than personal. This does not invalidate the concept, but it alters its meaning. Generation ships therefore change the question of interstellar travel. The original question asks how far a human can travel in one lifetime. Generation ships answer a different question entirely. How far can a civilization extend itself through time? This distinction matters. It clarifies why generation ships do not contradict earlier conclusions. They do not allow individuals to reach distant stars. They allow continuity across generations, trading personal experience for collective persistence. Seen this way, generation ships are not solutions to distance, but acknowledgments of it. They accept that space is vast and that time must be paid in full. Robotic probes already embody this principle in a limited form. They persist beyond human lifetimes, carrying instruments and messages outward. Generation ships extend that persistence to living systems, with all the accompanying complexity. Whether such ships will ever be built remains uncertain. The technological challenges are immense. The social challenges are even greater. Yet the physics does not forbid them. Understanding this brings calm realism. Interstellar space does not yield easily to speed. It yields only to patience measured in centuries and millennia. As you hold this perspective, the idea of travel subtly shifts again. Motion through space becomes less about reaching somewhere else and more about sustaining something fragile over extraordinary spans of time, drawing attention back toward the conditions under which individual human experience remains possible at all. You begin by noticing that your body never truly stops. Even at rest, cells exchange molecules, ions move across membranes, and chemical reactions proceed in careful balance. Life is motion at the smallest scales. Every attempt to extend human travel through time must contend with this constant activity, because survival depends on it. The idea of slowing biology is not imaginary. Medicine already uses controlled cooling to protect the body under specific conditions. When the body's temperature drops, chemical reactions slow. Heart rate decreases. Oxygen demand falls. This relationship between temperature and metabolism is well understood and described by physical chemistry. In hospitals, therapeutic hypothermia is used after cardiac arrest or traumatic injury. By lowering body temperature a few degrees, doctors reduce metabolic demand and limit damage to brain tissue. This technique buys time not indefinitely, but enough to improve outcomes. Cooling is carefully controlled, closely monitored, and reversed within hours or days. This medical practice demonstrates a real principle. Slowing metabolism slows biological time. Yet it also reveals the limits. Cooling too much disrupts cellular membranes, alters protein structure, and interferes with essential biochemical pathways. The body tolerates only a narrow range of temperatures before damage accumulates. Some animals extend this principle further through hibernation. Bears, ground squirrels, and certain bats reduce their metabolic rate dramatically during winter months. Heart rate slow. Body temperature drops. Energy consumption falls to a fraction of normal levels. These states are not passive. They are actively regulated through complex hormonal and genetic mechanisms. Hibernation is not sleep. It is a highly controlled physiological state shaped by millions of years of evolution. Cells in hibernating animals express protective proteins that stabilize membranes and prevent damage during cooling and rewarming. Blood chemistry changes to avoid clotting. Organs tolerate reduced oxygen supply in ways human tissues cannot. Even among hibernators, limits exist. Hibernation lasts weeks or months, not years. Periodic arousals occur, during which metabolism briefly returns to near-normal levels. These arousals appear necessary to maintain brain function and immune health. Time is slowed, not stopped. Humans do not naturally hibernate. Our physiology lacks many of the protective adaptations seen in hibernating species. Cooling a human body beyond modest levels leads quickly to arrhythmias, organ failure, and cellular injury. Attempts to induce deep metabolic suppression in humans face fundamental biological barriers. Researchers study ways to mimic aspects of hibernation using drugs that alter metabolism. Experiments in animals show partial success, temporarily reducing oxygen consumption and energy use. Translating these results to humans remains challenging. The complexity of human physiology resists simple modification. Cryogenics proposes a more extreme approach, cooling the body to very low temperatures, theoretically halting biological activity altogether. At sufficiently low temperatures, chemical reactions slow dramatically. Ice formation, however, becomes the dominant problem. When water freezes, it expands and forms crystals. Inside cells, ice crystals puncture membranes, disrupt organelles, and destroy structure. Preventing this damage requires replacing water with cryoprotectant chemicals that lower freezing point and reduce crystal formation. Cryobiologists studies these processes extensively. Small samples of cells, tissues, and embryos can be preserved at low temperatures using carefully controlled protocols. Even then, success depends on rapid cooling, precise concentrations, and limited size. Scaling these methods to entire human organs remains difficult. Preserving a whole human body presents orders of magnitude more complexity. Different tissues cool at different rates. Cryoprotectants must penetrate evenly. Toxicity becomes a concern. Rewarming must occur uniformly to avoid thermal stress and cracking. No method currently exists to freeze and revive a human brain without severe damage. Neural tissue is highly sensitive to structural disruption. Memory, personality, and identity arise from precise neural connections. Even small-scale damage can have profound consequences. Claims that cryogenic preservation can pause human life for decades or centuries remain unsupported by experimental evidence. No mammal has ever been revived after full cryogenic freezing. No complex organ has been restored intact after such treatment. This does not mean research is stagnant. Cryobiology continues to advance understanding of low-temperature effects. Preservation of organs for transplantation has improved significantly. These achievements extend hours into days, not decades into centuries. Hibernation-like states in humans are explored cautiously for medical and spaceflight applications. Short-term metabolic suppression could reduce resource needs during long missions. Even modest reductions would help. Yet these states would still operate on the scale of days or weeks, not years. Biology resists being paused. Life depends on controlled motion and balance. Removing that motion destabilizes systems in ways that cannot easily be reversed. Evolution has optimized human physiology for continuous operation within a narrow range of conditions. Time therefore remains active within the body, even when slowed. Cells accumulate damage from background radiation. Proteins misfold. DNA undergoes spontaneous changes. Repair mechanisms counteract these processes, but only when metabolism functions. Stopping metabolism removes repair along with damage. Cooling slows both, but does not eliminate the need for balance. Over long durations, even tiny imbalances matter. This reality places firm limits on how much biological time can be stretched. Humans can tolerate reduced activity temporarily. They cannot tolerate complete suspension without loss of structure and function. The appeal of cryogenics often arises from comparison with inanimate objects. Machines can be powered down. Data can be stored. Living systems differ fundamentally. They require ongoing regulation at every scale. In space travel, this means that biological presence cannot simply be frozen to bypass duration. Even if future advances improve metabolic suppression, they will operate within boundaries set by cellular chemistry and tissue organization. Shortening journeys remains more feasible than stopping time. Reducing exposure, improving shielding, and enhancing life support address duration without violating biology. These approaches respect the continuous nature of life. Understanding biological limits does not diminish curiosity. It grounds it. It clarifies why certain ideas remain impractical despite technological progress. It also highlights where effort yields meaningful gains. The human body is not fragile in the sense of being weak. It is fragile in the sense of being precise. Its stability depends on countless processes operating in harmony. Disrupting them completely removes the conditions for recovery. As this understanding settles, the idea of extending travel through biological suspension gives way to a quieter recognition. Time cannot be skipped. It can only be lived at the pace biology allows. In that recognition, attention naturally returns to what forms of exploration align with human physiology as it exists, and how knowledge, rather than presence, becomes the primary means of reaching beyond the limits imposed by living systems. You begin by returning to yourself as the reference point, not as an abstract observer, but as a living body with needs, limits, and awareness. Every question about distance ultimately resolves here, because travel is only meaningful if it is experienced. A place reached without perception, memory, or survival is not personally reached at all. To ask how far a human could personally experience space is to ask where motion, time, and biology still overlap. This overlap is narrow, shaped by constraints that have already revealed themselves through evidence and measurement. Speed determines how quickly distance is crossed. Biology determines how long endurance lasts. Energy and engineering determine how much speed and protection can be sustained. Begin with speed. Even with optimistic assumptions, human spacecraft operate far below relativistic regimes. Chemical propulsion defines the lower bound. Nuclear propulsion, particularly nuclear thermal systems, represents the upper bound of technologies grounded in tested physics and near-term feasibility. These systems could plausibly support sustained human missions beyond Earth orbit. With nuclear thermal propulsion, transit times to Mars could be reduced to roughly 3 to 4 months. This matters because shorter travel directly reduces radiation exposure, life support strain, and cumulative biological stress. Mars becomes not just reachable, but survivable with larger safety margins. Extend this same propulsion to other destinations. Near-Earth asteroids and some main-belt asteroids fall within similar or slightly longer timeframes. These journeys could be completed within a few years, including travel, exploration, and return. The human body can tolerate such durations with careful countermeasures, though not without cost. Beyond the asteroid belt, time stretches more aggressively. Jupiter lies several years away even under favorable conditions. Saturn lies farther still. These durations push against biological limits rather than immediately exceeding them. The challenge becomes cumulative exposure rather than acute risk. Radiation exposure provides a clear metric. Current safety guidelines for astronauts set career limits on radiation dose, based on increased cancer risk. Missions lasting several years in deep space approach or exceed these limits, even with shielding. Increasing shielding adds mass, which affects propulsion and system design. Bone density loss, muscle atrophy, and cardiovascular adaptation continue as well. Exercise mitigates decline but does not eliminate it. After multiple years, recovery becomes uncertain. Aging proceeds alongside these changes, narrowing the margin for safe return. Psychological endurance also matters. Multi-year isolation with communication delays imposes cognitive and emotional strain. While some individuals tolerate such conditions well, risk increases with duration. Human performance depends on sustained mental health, not just physical survival. When all these factors are combined, a practical envelope emerges. Missions lasting up to a few years remain within the outer bounds of personal experience. Missions lasting a decade push toward the edge of what can be managed, even under optimistic assumptions. Beyond that, the risks compound faster than mitigation strategies can compensate. Distance follows directly from time and speed. At velocities achievable with nuclear propulsion, a spacecraft might travel several astronomical units per year after initial acceleration. Over 5 years, this allows traversal of much of the inner solar system. Over 10 years, it extends toward the orbits of the gas giants. Yet arrival is not the same as experience. Reaching Jupiter's vicinity exposes crews to intense radiation fields that challenge survival itself. Even if travel time is tolerable, the environment at the destination may not be. This distinction matters. The farthest distance personally experienced is not the farthest distance physically reached. It is the farthest distance where presence remains viable, where eyes can see, hands can act, and memory can form without overwhelming harm. Under this definition, Mars stands firmly within reach. Certain asteroids do as well. Portions of the inner solar system up to the asteroid belt fall within plausible human experience given continued technological development. The outer planets occupy a transitional zone. They are physically reachable, but biologically hostile and temporally demanding. A flyby mission might be experienced, but a prolonged stay would likely exceed safe exposure limits. Beyond Saturn, the balance breaks. Travel time alone consumes a large fraction of a lifetime. Radiation exposure accumulates relentlessly. System reliability over such durations becomes uncertain. Even if arrival occurs, return may not be possible. Interstellar space remains decisively outside personal reach. Even the nearest stars lie thousands of lifetimes away at achievable speeds. No combination of propulsion, life support, or biological adaptation currently allows a human to personally experience another star system. This conclusion is not abrupt. It emerges gradually as constraints layer atop one another. No single factor forbids further travel. Together, they do. Energy limits propulsion. Propulsion limits speed. Speed limits time. Time limits biology. Biology limits experience. What remains is not disappointment, but clarity. The farthest distance a human could personally experience is not measured in light years, but in astronomical units. It is measured in years lived, not kilometers crossed. Within this boundary, exploration remains profound. The solar system offers diverse environments, histories, and phenomena. Human presence adds context and perception that instruments alone cannot replicate. Beyond this boundary, exploration does not end. It changes form. Robotic probes extend reach. Telescopes gather light across vast distances. Data flows inward even as bodies remain closer to home. This division is not a failure. It is a specialization. Humans explore where presence matters most. Instruments explore where endurance outpaces biology. As you sit with this understanding, distance feels less like a challenge to overcome and more like a framework to respect. Space does not demand conquest. It invites understanding within the limits of time and life. In this quiet framing, the question of how far one can go resolves into a gentler truth. The farthest meaningful journey is the one that allows awareness to remain intact, where travel enriches experience rather than consumes it, and where the vastness of space is met not with urgency, but with patience and care. You begin by noticing how questions change once limits are clearly understood. Earlier, distance felt like a challenge to overcome, a measure of how far technology might one day carry a human body. Now, with time, biology, and physics laid gently but firmly in place, distance becomes something quieter. It is no longer an obstacle demanding victory. It is a condition that shapes intention. Human space travel does not begin with rockets. It begins with curiosity. Long before engines existed, people looked up at the sky and asked what was there, how it worked, and what their place might be within it. This impulse was never about arrival. It was about understanding. When humans first left Earth's surface, they did not cross great distances. Early orbits remained close, looping around the planet every 90 minutes. Yet even these short journeys transformed perspective. Seeing Earth from above revealed patterns invisible from the ground. The thinness of the atmosphere, the continuity of oceans, the absence of borders. Distance mattered less than viewpoint. This shift in perspective remains central to why humans travel into space at all. Presence allows perception that instruments alone cannot fully replicate. The human brain integrates sight, motion, and context into a coherent sense of place. Even brief exposure can reshape how knowledge is understood. Walking on the moon did not answer new scientific questions that robots could not eventually address. Its deeper impact came from presence. Humans interacting directly with another world altered how the solar system was perceived culturally, psychologically, and philosophically. The experience mattered because it was lived. This distinction clarifies what human space travel is truly for. It is not about reaching every possible destination. It is about experiencing environments where presence adds value that cannot be transmitted fully through data alone. Robotic exploration excels where endurance and precision are required over long durations. Probes can travel slowly for decades, endure radiation without concern, and operate far beyond biological limits. They return measurements of extraordinary detail, expanding knowledge continuously. Human exploration excels where interpretation, adaptability, and contextual judgment matter. Humans notice unexpected patterns, respond creatively to anomalies, and integrate information across senses and experience. These qualities are most effective where communication delays are short and environments are survivable. This complementary relationship defines a natural division of labor. Humans explore where they can remain healthy, attentive, and safe. Robots explore where distance and duration exceed human tolerance. Together, they extend understanding farther than either could alone. The urge to frame exploration as competition between humans and machines misses this balance. Machines do not replace human presence. They extend it conceptually, gathering information that informs where presence is most meaningful. Within the solar system, human travel retains a clear role. Orbiting Earth, visiting the Moon, traveling to Mars, and potentially exploring nearby asteroids all offer environments where direct human experience deepens understanding. These destinations lie within timescales that allow learning, memory, and return. Beyond this region, personal presence yields diminishing returns relative to risk. Time spent traveling dominates time spent observing. Biological stress accumulates. Communication delays widen. In such contexts, robotic systems become the appropriate extension of curiosity. This realization reframes ambition. Exploration is no longer about pushing bodies to the furthest possible edge. It is about choosing where bodies belong and where instruments suffice. Perspective also reshapes how success is measured. A mission does not need to cross vast distances to be meaningful. A few hundred kilometers above Earth can be transformative. A few days on another world can alter understanding permanently. Space travel, then, becomes a way of learning how to see. Seeing Earth as a planet among planets. Seeing gravity as a sculptor of motion. Seeing time as a factor that cannot be ignored or bypassed. This way of seeing feeds back into life on Earth. Satellite observations improve climate understanding. Orbital platforms enable medical and materials research. Technologies developed for space support often return benefits in energy efficiency, communication, and environmental monitoring. Yet the most profound contribution remains intangible. Perspective changes values. Fragility becomes visible. Scale becomes intuitive. The realization that Earth is small, finite, and interconnected reshapes how responsibility is felt. Human presence in space reinforces this lesson in ways data alone cannot. Knowing intellectually that the atmosphere is thin differs from seeing it as a narrow blue arc against darkness. Understanding climate models differs from watching cloud systems move across an entire hemisphere. This is why presence matters where it is possible. It grounds abstraction in experience. It turns numbers into understanding. As limits become clear, space travel sheds the language of conquest. There is nothing to conquer. There are only environments governed by physical laws, indifferent to ambition but responsive to careful interaction. This shift brings calm. Exploration no longer demands urgency. There is no race against distance. Knowledge accumulates patiently, observation by observation. Time itself becomes an ally rather than an enemy. Human lifetimes are short relative to cosmic scales, but long enough to contribute meaningfully. Each generation adds clarity, building on what came before. Seen this way, the inability to reach other stars personally is not a loss. It is a boundary that focuses effort where it matters most. It channels creativity into understanding rather than endurance alone. The stars remain accessible through light. Telescopes gather photons that have traveled for years, centuries, or millennia. Spectra reveal composition. Motion reveals mass. Planets are detected through subtle effects measured across vast distances. This knowledge is real. It does not depend on physical arrival. In many cases, arrival would add little to what careful observation already provides. Human space travel therefore exists not to replace astronomy, but to complement it. Presence enhances understanding where proximity allows. Observation extends understanding where it does not. This balance aligns with the nature of curiosity itself. Curiosity seeks truth, not possession. It asks how things work, not whether they can be reached. As you sit with this perspective, space feels less distant and less demanding. It becomes a structured environment governed by laws that can be learned, respected, and navigated thoughtfully. The question of how far humans can travel resolves into a deeper question of why travel at all. The answer lies not in distance, but in perspective gained. Human space travel is truly for learning how to see more clearly, how to place ourselves within a universe that is vast but comprehensible, and how to return with insight that reshapes understanding at home. In this quiet resolution, exploration continues without strain. Bodies travel where they can thrive. Instruments reach where bodies cannot. Knowledge flows inward steadily. The universe remains vast, but no longer overwhelming. It does not need to be crossed in full to be understood. It only needs to be approached with patience, precision, and respect for the limits that make meaning possible.